Okay. So we've already done a lot of classes in image enhancement in class. We've done to a point where we were discussing about logarithmic transformations. We talked about image negative, where I showed you Python Anaconda how you can take the negative of an image. But for today's class, we'll redo what we've just done in class, and this is especially for my class image processing students. What is image enhancement? So whenever there is an image and somehow the visual interpretation, when you look at an image and you are unable to interpret an image and you want to improve that image so that the visual interpretation is enhanced, that would be termed as image enhancement. So if you've got an image and that looks really dark and you want to brighten it up, at least you feel that image is looking visually correct, then simple step is termed as image enhancement. There are many methods of image enhancement. Some are very simple and easy to implement. Some are really complex and difficult to implement. But nonetheless, all of them are very subjective. They are not quantitative. As such, when you process an image, how much should the image be processed is subjective. It is entirely upon the analyst or the person who's viewing the image. If I'm viewing the image and I feel the image is good, that amount of pre-processing or that amount of image enhancement is enough. Wait up. Okay, so here you go. Yeah. Okay, so normally when you do image enhancement, it is also called as pre-processing. So what are the different image enhancement methods available? Recap. Okay, something's happening, I really don't know. Okay, so if you can recapitulate what had happened or what we studied so far. An image is but a matrix of values. So if it is a grayscale, if it is a gray image, an image that has only values, different shades of gray, like in this case. So these are the rows and these are the columns. This is what an image would look like. Not that it has only 5 rows and 5 columns, but this is for the simplicity. We've got 4 rows and 5 columns. This is an imaginary image. And we've got 1, 2, 3, 4 different images with 4 rows and 4 columns. Now each value in each pixel will tell you the intensity of this gray value. Okay, it will tell you the intensity of the gray value. So if there is a 0 in a pixel, it means it is black. And as and when you increase the pixel values, depending upon the radiometric resolution, radiometric means how each pixel is represented by how many bits. So in our example, each pixel in image is represented by 8 bits. So we'd seen 2 to the power 8. 2 to the power 8 would be 256 different values. So had it been, so we've got different images, 8-bit images, we've got 12-bit images, we've got 16-bit images. So this is an 8-bit image. So 8-bit image will, how many values can you store in an 8-bit image is? We can have 2 to the power 8, that means 256 different values. So each value in a pixel can range from 0 to 255. So hence you can see an 8-bit image will have, one pixel can take up any values between 0 and 255. So if a pixel has a value of 255, it means it would display white. If you put a gray color over this, of course, because these are only numbers, so these are not colors. So if you were to distribute colors over these numbers using lookup tables, so these are numbers. So if you say, okay, 0 is going to be black and 255 is going to be white, and all in between are going to be different shades of gray. So depending upon the value of the number, the color gets distributed. Okay. So then after that, we've wait. Okay. So this is what an image looks like. I'm sorry. And we've got three different image processing can happen in three different domains. One is the spatial domain, where all the image enhancement takes place in the pixel values itself. And you've got frequency domain, where we've talked about how we can take this image and we transform this image into a frequency domain. How do you do that? We've already talked about this in the class. You take this image and perform a Fourier transform. Fourier transform can be performed by DFTs or FFTs, fast Fourier transform. These are methods. Once you take the Fourier transform of an image, when you take a Fourier transform of this image, and we perform the transformation, we perform the enhancement in the transform in the Fourier transformed image, and after that again we take the inverse of that image and we come back to the spatial domain. So in spatial domain enhancement, we perform enhancement on the image. But when we talk about Fourier transform enhancement, frequency domain enhancement, we have to change this image from the spatial domain by using Fourier transform. The image gets changed to a frequency domain. There you apply the transformation, and once the transformation is finished, again you perform the inverse Fourier transform, and again you come back to the spatial domain and you can display the image. So that is another aspect of frequency domain. And then you can have yet other images which can combine spatial and frequency domain images. Okay. So we need to first see the taxonomy. So image enhancement, before we talk about image enhancement, we're only talking about image enhancement in spatial domain. We are not talking about image enhancement in frequency domain for this part of the lecture. So there are many kinds of methods in the spatial domain, especially pertaining to image enhancement in the spatial domain. So these are the various methods. The spatial domain can be grouped into contrast stretching, where we stretch the contrast, and this is what we're going to see in this class, in this particular lecture. So what are the different enhancement that can happen? What are the different enhancement if there is an image? This is a grayscale image, and we're talking about making some changes on the pixel itself, not on the frequency domain, on the spatial domain. So what are the different techniques that we can use to change this image, to make this image more visible? The first one is called your contrast stretching. Now we'll see what a contrast is, we'll stretch the contrast, and we'll see how it is enhanced. And the contrast stretching, when you talk about contrast and we try to enhance the contrast of an image, they fall under two categories again. There is linear contrast stretching, and if there is a family of methods where you can linearly stretch a contrast, there will obviously be a family of methods that you can non-linearly stretch a contrast. So some of the non-linear contrast stretching is something we've already seen in class. Log transformation, where we've seen a curve, if you remember, where the lower part of the grayscale values were enhanced to brighter images. Then there is thresholding. So today's class we'll be seeing this linear contrast stretching altogether. We'll see one example of nonlinear histogram equalization. There are other techniques of thresholding. Then you've got image negatives. We've seen an image negative example in class, if you remember. And in the next section we'll talk about the spatial filtering. Okay, so again, before we begin the class, if you remember, I'd shown you in class about what an image is all about. So I'd opened up my Jupyter notepad in the Anaconda environment, where we had taken, we'd called in this SK image. SK image is scikit-learn image processing library for Python, and we had also imported a matplotlib. This is another library for plotting graphics in Python, and we'd use this matplotlib, this data from the SK image. So SK image has a lot of data, already pre-installed pictures. So from this data we'd taken an astronaut and we'd seen an image, and we'd seen that an image has a lot of pixels made out of different values. for gray images. For color images, we had 3 bands, 3 channels. So if you can see, the same astronaut, this is a color image. From the color image in class, we had taken out, we'd convert this color image into only one single image called the gray image, RGB to gray. We converted this color image to a gray image, and then we displayed the gray image, we displayed the color image, and we'd seen the value. Now if you just bear with me and see this, the output of this program we've seen in classes, the color image we've converted into a gray image. So a gray image does not necessarily look gray. It has only one mono channel. It only has a matrix of values, only one matrix of values. When you talk about a color image, it has 3 different matrix of values. So when you talk about this gray image, we've converted this color into one gray. We converted this color into one gray image. So this gray image is having one matrix of values, and over this values, if you throw a gray color, it will have a gray impact. But if you throw a red color, this is what it will look like. So if you can see, the code here is, I'm trying to show, I'm going to plot the gray image, but on top of the gray image, I'm throwing off a red color map. So whichever values have 0 is coming out to be very red, and whichever values have 255 it's coming up very bright. And the similar color images here, just to understand that a color image can be converted into a gray level image, and a gray level image does not necessarily have to look gray. You can, it is only values, okay, it is only one matrix of values. You can throw in a green color, you can throw in red color, but based on the pixel intensity, that color intensity will magnify. And this is the matrix we've displayed for this for the red image, for the color image. So there are, it is an n-dimensional matrix. If you can see, the size of this image was the size of this color image was 512 length, 512 breadth. There are 512 pixel rows, 512 pixel columns, and there were 3 bands. It's very visible here. And then if you see the grayscale image, the grayscale image will have not an n-dimensional matrix, of course. So it is only one band. There's only one band, and then the grayscale is again shown, but with a different color altogether. So let's begin the class. I hope I have captured all the previous classes that we've done, and we've talked about if you recapitulate again, spatial domain, again, when you do enhancement in spatial domain, we are not doing enhancement in frequency domain. We are doing enhancement in spatial domain for now. And in spatial domain, again, there are 2 kinds of processing. The first one, as you can see, is called point processing, where we process each pixel one at a time. So if there is an input pixel, if there is an input image, if this is an image, and we process one pixel and we take out a corresponding output, we process another pixel, we take out a corresponding output. So that when you process it pixel by pixel, it is called point processing. On the other hand, if we take one group of pixels and we process it, and based on this group of pixels we find out a value for one pixel, that is called neighborhood processing. Okay, so if one pixel input and one pixel output, that is point processing. If there's a group of pixels deciding for one input, so if my neighbors decide for my value, that is called neighborhood processing. If I decide for my value, it is point processing. So a spatial domain equation can be written something like this, where G is the output image and the output image, so X and Y. So X is the column, Y is the row. So G is the output. So if you vary xi, yj, if you keep varying xi, yj, you will get all the pixels in the output image, and fxy is the input image. So there is an input image. For every pixel in the input image, for a group of pixels in the input image, if you apply some transformation, you get an output G of XY. This is what we've done in the class, where it's written here, fxy is the input image, gxy is the processed image, and t is the operator for fx and y. So what I've mentioned is here exactly. So this is an example. So this whole is an image, and we are considering this particular point x and y at this current position. So we want to enhance this pixel. So when you enhance this pixel, the value of this pixel is decided by decided by some kind of computation, or is influenced by the computation that involves all of its neighboring pixels. So this is a 3 by 3 pixel. So this whole for this pixel there is 3 rows and 3 columns. So for this x and y pixel, if the value of this x and y pixel depends upon all of its neighborhood, then it is called neighborhood processing, of course. So then this window, this 3 by 3 window, keeps shifting to the left. Then this window decides for the next pixel. Again, this window shifts to the left. Again, it decides for the next pixel. So the point that I'm trying to make is, if each input pixel is processed based on its neighborhood, then it is called neighborhood processing. But if this neighborhood is 3 by 3, so if this neighborhood decreases and it becomes 1 by 1, if it becomes 1 by 1, which means only a single pixel value, if it becomes a single pixel value, then it is called a point processing. So तपाईको यो neighborhood जुन छ यो 3 by 3 नभएर 1 by 1, only x and y मात्रै छ रे. So x and y लाई enhance गर्न x and y मात्रै चाहिन्छ भने only this your point P, if you need only this point P to process only this point, it's called point processing. But to process, what's wrong? To process this pixel, if you need all its neighborhood, then it's called neighborhood processing. So neighborhood can be 3 by 3, 4 by 4, 5 by 5. We will see this later on, but not now. So similarly, if you can see, so when so if it is a neighborhood processing, the equation of transformation takes this place. It takes the form of gxy equals to t of f and xy. Okay, so is there any questions so far? So if there's any questions, I can take it up now. Otherwise we proceed. Okay, so before we proceed to another class, it's very important to know what is an histogram and what is contrast fetching, because what we're going to learn today is we're going to learn linear contrast fetching. We're going to learn linear contrast fetching. It is one of the methods of image enhancement in spatial domain. We're going to see what is min-max contrast fetching, percentage linear contrast fetching, standard deviation piecewise, and histogram, thresholding, and many others. But before we begin, we got to know what is histogram, because somewhere we've seen histogram equalization. Here you go, histogram. What is an histogram? What is histogram of an image? Somewhere we see contrast. What do you mean by contrast? Somewhere we see linear. What is linear? Somewhere we see stretching. What is stretching? So let us do the preliminary class before we begin. So we need to know about histograms. So a histogram is a frequency distribution chart, a picture. When you take a graphical representation, if this is a picture, and if you can represent this picture based on its frequency of occurrence, if I simplify that, which values in a pixel occur how many times, the frequency distribution. So say for example, if one pixel has a value 1, gray level 1, so how many times does the gray level 1 occur in an image is what the frequency tells you. So if you can see in this image of this histogram, the 0 to 255, so this is the input image, 0 to 255. So you can see 0 देखि अलिकति अगाडि आएर, if you can see this, if I can enlarge this somehow, okay, so 0 देखि अलिकति अगाडि आएर, so say for example 10, so the pixel value 10 is occurring कति ताल, if you can see it's quite high. So maybe this is maybe 500. So 500 pixels have the value 10. Similarly, say, so 0, this is 255, so this is somewhere in the middle, say 150. So the gray level 150 is occurring how many times? Maximum times. So the maximum could be 255, or probably not 255, it could be, frequency could be 1000. So 1000 pixels in an image have the value 150. So this histogram tells you the distribution, the frequency distribution, how many times a certain pixel value is occurring in an image. Now, the histogram of a digital image is a distribution of its discrete intensity levels in the range of 0 and 1. Okay, so this is 8-bit grayscale image. The distribution is a discrete function h associating to each intensity value rk, the number of pixels. Okay, so h is the histogram frequency. H is the histogram frequency. This side is your h of rk, and which tells you the number of intensity values. So why is there a need for histogram? So when we take an image and we look at it, we can't clearly identify if the image is good or bad. Sometimes, most of the time, it's very visually evident that the image is not correct. But sometimes when you click an image, even when you're in DSLR cameras, when you click an image, you probably, even if on your phone, if you click an image, then you see that sometimes the image is okay, but you really don't know if it is really okay, technically speaking. So in DSLR cameras, you have this option of looking at a histogram. Even in Photoshop, if you import an image, and then there is a provision, a property of that image where you can view the histogram of an image, and the histogram tells you a lot about an image. So if you can see from here, if this is an image, this is a dark image, you can see, and the pixel values in this input image, it's an 8-bit image. So this is a matrix of values. So all the values in this image can take up any values from 0 to 255, because that is the range. That is what we call as radiometric resolution. So 8-bit, it's an 8-bit grayscale image. So 8-bit is to the power 8, is 256 different levels. So 256 means 0 to 255 different gray values. So this image has the capacity to take up any of the values from 0 to 255. So now this is visually okay, but when I look at the histogram and I see that the histogram of this image has taken up values only between 0 and half of 255, so that would be around 100, 150, yeah, 110. So from 0 to 110, this image has taken up values from 0 and 110. And if you can see, there are 3 different spikes. So if in statistics, when there is a curve, when there is this frequency distribution and it has many highest points, so these are known as modes. So this is one mode, this is one mode, this is another mode. So it has 3 different modes. So this particular histogram is a multimodal histogram. Okay, so it is not a single mode, it's a multimodal histogram. So multimodal histogram, what does it tell us? It tells us like there are 3 distinct colors, objects or colors in an image. So probably this black one, this black image at the side is signified by this portion here, because 0 means black, yeah, and a lighter part of this gray is signified by this peak, and some values, this value is a little less, and then again brighter values corresponding to not the whitest part, but the middle 110 values are again maximum. So I think this is it involves this light color, light grayish in between black and white. So there are 3 multimodal. So because this image has taken up pixel values only between 0 and 120, the contrast is not there. That's what we mean. The difference between all these values is not there. So it's not very pleasing to the eye. So if you can make this picture, or the pixels in this picture, take up all the values between 0 and 255, keeping the nature of this multimodal curve the same, in the same proportion, if you can increase, it's like clicking my picture, passport picture, and expanding it. My proportion remains the same, but I become bigger. So same, keeping the proportion, the properties, the three peaks the same. If we can make this image take up this entire dynamic range of sensitivity, then the contrast increases and the image will become better. So if you can see here, this image is particularly high contrast. So this image has taken up the entire range of input intensity values from 0 to 255. So suddenly you can see it's a far better picture than the others. Now here you can see now. So this picture, entire pixels are towards the lower half of 255. So obviously it becomes a darker picture. Yeah, and have a look at this image now. The same image, you increase the brightness, the overall pixel intensity, and the shape of the multimodal frequency distribution remains the same, but now all of them have shifted towards the upper half of 255, from 110 to 255. So all those frequency distribution that lie towards the extreme right would be brighter images. All those images that whose frequency lie towards the left are darker images. All those images whose frequency distribution take up the entire range of the dynamic range from 0 to 255 are very good contrast. And sometimes you may click a photograph where it seems to be very low contrast. Low contrast means this whole image is defined by very small different values. The different values in this pixel, the pixel is defined by different values. This black has different value, white has different value. So the ratio between the different values is very small. So your pixel ma, your whole pixel banako cha khali maybe 3 pixel values, 5, 10, 15, 5, 10, 15, 5, 10, 15 le garda. Only 3 values le banayo bhane this range becomes very small. So when the frequency range, dynamic range is very small, it is called very low contrast. So if this image was made by different values from 0 to 55, some are 10, 20, 50, 200, 210, then this becomes a high contrast image. So that is what is histogram. Then the next question, obviously, after we understand what is an histogram, is what is contrast. So I've already said a few. We've already discussed a few about what do you mean by contrast. Now look at this image. The image on your left hand side or your right hand side, I'm not sure, is an image that has low contrast. So that means usko dynamic range is very small. Yeah, response, excuse me.